Next time you're on a flight, look out the window at the wing. It's bending. Right now. Several feet up and down with every gust. A structure the length of a 7-story building flexing like a diving board. And here's the part that should stop you cold. If it didn't flex, if that wing were perfectly, completely rigid, it would likely snap clean off. The thing keeping you in the air isn't rigidity. It's controlled movement. And the story of how we learned that lesson is written in wreckage. A Boeing 787 Dreamliner has a wingspan of nearly 200 feet. That's longer than the Wright brothers' entire first flight. At cruise, each wing is generating enough lift to support the weight of roughly 150 family cars. Continuously, for hours. The forces involved aren't gentle. Turbulence alone can subject a wing to load changes equivalent to slamming the brakes on that 150-car stack. Repeatedly, unpredictably. During extreme certification testing, Boeing's engineers bent the 787 wing upward by 25 feet before stopping the test. Not because it broke, but because the test rig ran out of range. The wing hadn't failed. A structure the size of a building, carrying forces that dwarf anything in your experience, bending a quarter of its length and returning to position. This should not work. But it does. Because of a principle engineers spent decades learning the hard way. In the 1940s and 50s, as aircraft pushed faster and higher, engineers discovered a problem with a brutal name: metal fatigue. A rigid structure under repeated stress doesn't fail all at once. It develops microscopic cracks, invisible, silent, accumulating with every flight cycle. Until one cycle, the crack is just long enough, and the structure fails catastrophically. The de Havilland Comet, the world's first commercial jet airliner, was destroyed by this. 3 aircraft broke apart in flight between 1953 and 1954. Investigators traced the failures to stress concentrations around windows and rigid structural joints where forces had nowhere to go except into the metal itself. The lesson was fundamental. Rigid structures don't eliminate stress. They concentrate it. And concentrated stress, repeated enough times, always wins. The answer wasn't stronger metal. It was smarter structure, one that moved with the forces instead of fighting them. Here's all you need to understand this. Think of a tree in a storm, a rigid tree. Concrete post, no flex, either holds perfectly or snaps. There's no middle option. All the force concentrates at the base. A living tree bends. The energy of the wind distributes across the whole structure. Trunk, branches, every point of flex. No single point takes the full load. The tree survives by sharing the stress. Aircraft wings work on exactly this principle. Flex isn't a weakness in the design. Flex is the design. It's the mechanism by which catastrophic stress concentration is prevented. The wing isn't failing when it bends. It's doing its job. Picture this. You hit turbulence at 35,000 feet. A gust punches upward against the wing. A sudden, massive load increase. In a rigid wing, that force has one place to go, straight into the joint where the wing meets the fuselage. Every pound of that gust concentrated at one point, thousands of times per flight. In a flexible wing, something different happens. The wingtip rises first, absorbing and redistributing the energy across the full span. The load travels inward gradually, spread across hundreds of feet of structure. By the time it reaches the fuselage joint, it's a fraction of what a rigid wing would experience at that same point. Think of it like catching a ball. Catch it with a locked, rigid arm and the impact slams straight into your shoulder joint. Catch it with a bent, giving arm and the same force spreads across your wrist, elbow, and shoulder, none of them taking the full hit. The flexible wing is the bent arm. The rigid wing is the locked one. But here's where it gets interesting. The flex isn't passive. Modern composite wings, like those on the 787 made from carbon fiber rather than aluminium, are engineered to flex in very specific ways. The material is layered at precise angles so the wing bends upward under load but resists twisting. Twist would change the wing's angle of attack mid-gust, potentially making the aerodynamics unpredictable. The flex is shaped, directional, intentional. It's not a wing that tolerates bending. It's a wing that uses bending. Most people don't realize. The 787's wings are so flexible that during that certification test, the 25-foot bend, the wingtip was higher than the tail of the aircraft. Engineers watched a wing designed for passengers fold upward into a shape that looks structurally impossible. It returned to position perfectly. Here's what almost nobody thinks about. Fuel lives in the wings. A fully loaded long-haul aircraft carries over 100 tons of fuel distributed across both wings. That weight actually helps. It acts as a counterbalance to the lift forces trying to bend the wingtip upward. Heavier wings flex less. As fuel burns during flight and the wings get lighter, the ride can actually get slightly rougher. The passengers notice. The engineers planned for it. And this detail is quietly brilliant. When a flexible wing bends upward, it slightly changes the geometry of the entire aircraft's aerodynamics, reducing induced drag in the process. The flex isn't just absorbing stress, it's improving efficiency at the same time. The 787's winglets, those curved tips, are designed specifically to maximize this effect. The wing is most aerodynamically efficient at its most stressed. Here's the simple truth underneath all of it. Rigidity feels like strength. It looks like confidence. We build rigid things when we want them to last. But the real world doesn't deal in steady, predictable loads. It deals in gusts, turbulence, and forces that arrive from unexpected directions at unexpected magnitudes. Against those forces, rigidity is a liability. It concentrates what it should distribute. The wing that bends 25 feet and returns to position isn't compromised. It's honest. It's built for the world as it actually is, not the world we'd prefer it to be. That's not just good engineering. That's a lesson that applies further than aviation. Now here's something even more interesting. The wings flex, but the engines hanging under them don't. They're attached by pylons specifically designed to detach under extreme impact rather than transfer force into the wing. They're engineered to fall off safely. Why, that's actually the safest possible design. And what happens when it works exactly as intended? That's the next video. Subscribe to stay tuned.